I welcome you to another lesson on discrete mathematics. In this video lesson, we'll understand how to solve a recurrence relation, which can be used to identify the pattern in a sequence and express it in an efficient form. Recurrence relations help us express the terms of a sequence in a very concise manner. For example, we can consider this sequence containing the terms 1, 7, 25, 79, etc. The terms of the sequence can be defined using the recurrence relation. S of n is equal to 3 times S of n minus 1 plus 4, along with the initial condition which says S of 0 is equal to 1. Now, as long as we know S of 0 is equal to 1, I can determine S of 1 as 3 times S of 0 plus 4, which is 3 times 1, 3 plus 4, and 7. This is what we have here. And if we know S of 1, we can find S of 2 as 3 times S of 1 plus 4, which is 3 times 7 plus 4, which is 21 plus 4 at 25. Likewise, if I know what the n minus first term is, I can define S of n based on this recurrence relation. We call such recurrence relations as of first order because we need a maximum of one term to define the recurrence relation completely. If you can look at this, S of 0 is equal to 1 is all the information we need to start building the sequence. This term is necessary to build the sequence, and only this term is enough. Such recurrence relations are said to be linear recurrence relations of first order. Linear because the powers of the terms here are ones, and first order because only one extra information is necessary to completely define the sequence based on the recurrence relation. Another clue that you can take up is that the order can also be identified by the smallest term that is part of the definition. When I say S of n is 3 times S of n minus 1 plus 4, the smallest number here is n minus 1, and this 1 can be connected with the order of the recurrence relation. The next thing we look at is to solve the recurrence relation. Solving the recurrence relation means that we have derived a closed form expression of S of n. By closed form expression, we refer to a function in n which depends only on n and not any terms of the sequence. For example, the same recurrence relation that we have taken up here can be solved and expressed in the form of this closed form expression, which is 3 times 3 power n minus 2. If I have this equation, I can directly find S of 2 just by using 2 in the place of n, which means I'll just get back 3 times 3 squared is 3 times 9, 27 minus 2, which is 25. The same 25 that we obtained using S of 1 can be obtained without even actually finding what S of 1 is. Such an, such an expression is what we call as a closed form expression. So throughout this video lesson, we'll focus on how to solve a given recurrence relation and obtain its closed form expression. The first example that we'll discuss is a recurrence relation of this kind. S of n minus 17 times S of n minus 1 plus 70 times S of n minus 2 is equal to 0. This recurrence relation has two conditions given along with it. They are S of 0 is negative 2 and S of 1 is 13. We can rewrite this recurrence relation in this form. S of n is equal to 17 times S of n minus 1 minus 70 times S of n minus 2. And we see that it is a homogeneous recurrence relation of order 2. We know why it is of order 2 because the smallest number involved is n minus 2. So this 2 here will give us the clue that it is of order 2. Further, we also call it homogeneous because the function the given expression S of n depends only on S of n minus 1 and n minus 2, but no other function of n. It doesn't depend on any function of n. Or if there was a notation expressing the function of n, that takes the value 0. Such functions are called as homogeneous linear recurrence relations. Solving homogeneous recurrence relations is pretty simple. We just need to express the same recurrence relation in terms of an algebraic equation. That's obtained by identifying the order. We have identified the order of this recurrence relation as 2. Therefore, we just replace S of n by r square, the algebraic term, S of n minus 1 by r to the power of 2 minus 1, and S of n minus 2 by r to the power of 2 minus 2. This means our recurrence relation will get simplified as r square is equal to 17 times r power 1 minus 70 times r power 0. That simplifies down to r square minus 17r plus 70 is equal to 0. This is what we call as the characteristic equation of a recurrence relation. Identifying the characteristic equation of a recurrence relation helps us solve it without greater difficulty. We easily solve this as long as we are identifying the equation correctly. Once again, I tell you, as soon as we know what the order is, we can define the characteristic equation in this manner. So now we have identified the characteristic equation. This forms step 1 of the solution. So we have identified the equation as r squared minus 17r plus 70 is equal to 0. And we try and solve this quadratic equation. The two roots that we get are 7 and 10. Now, based on these roots, we define the homogeneous part of the solution, which is SH of n, as a times 7 power n plus b times 10 power n for arbitrary constants a and b. Now, we call this as the homogeneous part because this part of the solution takes care of only the left-hand side of the recurrence relation. Of course, there is no term on the right-hand side, so this will, in fact, form the entire solution, but we're just making note of it here. So the general expression to find the homogeneous part of the solution is based on the nature of the roots. If the roots are distinct, if the roots of the characteristic equation are distinct, then the homogeneous part of the solution can be expressed as a times r1 power n plus b times r2 power n, where r1 and r2 are the roots. R1, R2 are roots of the characteristic equation. In case the roots are identical, let's say the roots are identical, then the corresponding homogeneous part of the solution can be expressed as a plus bn times r to the power of n. Once again, a and b are arbitrary constants. In our case, we see that the roots are real and distinct, which means the homogeneous part of the solution will take this form. So we have the answer. This is the general solution of the recurrence relation. The answer will be more accurate and particular if we can find the value of the constants a and b. We'll do that using the information given in the question. The question says, if n is 0, the sequence takes the value minus 2. So when n is 0, we have minus 2 as the answer. Therefore, we'll replace n by 0 throughout this answer given here and get one equation. So a times 7 power 0 plus b times 10 power 0 is negative 2, which means a plus b is minus 2. That's equation number 1. And similarly, we also know that if n is 1, S of n takes the value 13. So when you replace n by 1, we have a times 7 plus b times 10 is equal to 13. So 7a plus 10b is equal to 13. That's our equation 2. Now we have a nice system of two equations in two unknown variables, which can be solved to obtain the values of a and b. We'll do that on the next slide. So we have a plus b is negative 2 and 7a plus 10b as 13. We can solve this and we can get the value of b as 9. Once we know the value of b, we can substitute this in any of the two equations and get the value of A as negative 11. So this means the homogeneous part of the solution, and in this case, the complete solution of the recurrence relation is negative 11 times 7 power n plus 9 times 10 power n. Kindly note that this solution is in the closed form expression of the sequence. Closed form expression. Why is it closed? Because the answer depends only on n and not on any term of the sequence. If we know what the value of n is, we can completely find s of n for any value of n. So we have obtained the closed form expression, and that means we have solved the recurrence relation on hand. Once you have obtained this, the recurrence relation has been solved. I'll just give you a way to verify how this answer of ours is correct. So we start by finding S of 2 using the equation that we have just defined. So we'll use 2 in the place of n in our equation. So S of 2 is equal to negative 11 times 7 squared. Just note how I've replaced n by 2 here and 9 times 10 squared here. So that's negative 11 times 49 and 9 times 100, which simplifies down to 361. The S of 2 appears to be 361, but we just find out if that is right by using the question. The question showed us that S of n was 17 times S of n minus 1 minus 70 times S of n minus 2. Using 2 for n means that we have 17 times S of 1 minus 70 times S of 0. Since S of 1 was 13 and S of 0 was negative 2, we substitute them in the equation and we see that S of 2 is also 361. So the answer we obtained from our answer matches the answer we obtained from the question. Both answers match, and hence our answer, which we just defined a couple of slides back, this answer is in fact correct. So that explains how to solve a linear homogeneous recurrence relation of order 2. Yes, the next problem that we'll discuss is another homogeneous linear recurrence relation. Let's have a look at the question. We have S of n minus 12 times S of n minus 1 plus 36 times S of n minus 2 is equal to 0. Two things to note about this recurrence relation is that it is of order 2. Why do we know this is of order 2? The smallest term in the recurrence relation is n minus 2, and this 2 gives us the clue that it is of order 2. And second, it is also homogeneous because we do not have any function of n on the RHS of the equation. That tells us that this recurrence relation is of homogeneous nature. We are also given two information in addition. S of 0 is given to be 4 and S of 1 is given to be 36. Let's go ahead and solve this. The first task will be to define the corresponding characteristic equation. So we do that by replacing S of n by r square, S of n minus 1 by r power 2 minus 1, and S of n minus 2 by r power 2 minus 2. So we have r squared minus 12r plus 36 is equal to 0. We see that the two roots here are real and distinct, and therefore we'll have the corresponding recurrence relation of the form a plus bn to the power of a plus bn multiplied by 6 power n. The solution is complete if we can find the values of both a and b here. Let's start that. To find the values of a and b, of course, we'll use the constants given in the question. S of 0 is given at 4, S of 1 is given at 36. We'll do that on the next slide. So we have when n is equal to 0, we have SH of 0 is equal to 4. So a plus b times 0 into 6 power 0 is 4, or a times 6 power 0, which is just 1. A times 1 is 4, and we have the value of a as 4. Similarly, when SH of 1 is equal to 36, we have a plus b times 1 into 6 power 1 is 36, or that's simply 6a plus 6b is 36. Simplifying, we say that b is 2. We see that b is 2 and we obtain a as 4. Now that we know both A and B, we have the complete solution of the recurrence relation in the form that is expressed here. So that's 4 plus 2n times 6 power n appears to be the complete solution. Once again, we note that this answer is the closed form expression of the corresponding sequence because it depends only on n and not on any other term of the sequence. Once again, we'll just do a small exercise and verify if this answer is right. We'll just use 2 for n and find out the answer for s of 2. When s of 2 is to be determined, we have 4 plus 2 times 2, which is 4 plus 4 times 6 power 2, which is 36. That's 8 times 36, which happens to be 288. Now, this is the answer that we obtained from the closed form expression. We'll compare this with the answer that is possible from the actual question. So we have 288, and the question was s of 2 is equal to 12 times s of 2 minus 1 minus 36 times s of 2 minus 2 when n is equal to 2. So that's 12 times s of 1, which is 12 times 36, minus 36 times s of 0, which is 36 times 4. So 432 minus 144 also happens to be 288. So the answer we obtained from the closed form expression matches the answer we obtained from the given recurrence relation. Therefore, the answer we obtained here using the solution here is the correct answer. The correct solution is the solution of the RR. We'll go to another problem, slightly different type here. All right. Let's identify the order and nature of this recurrence relation. The first thing that we note is that this is also of order 2. Why is this of order 2? The smallest term in the sequence is having n minus 2 in its definition. Therefore, it is of order 2. Secondly, it is non-homogeneous. Why is this non-homogeneous? We see that S of n can be defined as S of n actually takes the form S of n minus 10 times S of n minus 1 plus 24 times S of n minus 2 is equal to 30. So here we have a function as part of the recurrence relation. S of n depends not only on the previous terms but also a constant. Therefore, it is not homogeneous and it is of order 2. We also have two extra pieces of information, the answers for S of 0 and S of 1. So we'll go about and start solving this recurrence relation by first finding its characteristic equation. So as usual, we'll replace S of n by r square, S of n minus 1 by r, and S of n minus 2 just by the constant. So we have r square minus 10r plus 24 is equal to 0 as the characteristic equation of the recurrence relation. And that's our first step. So we have the equation we can solve. We see that the roots of this equation are 4 and 6, both of which are real and distinct. Therefore, the solution of the homogeneous part of the recurrence relation. Since this is non-homogeneous, our answer will be of two parts. One, the homogeneous part, and one, the particular part. The homogeneous part is obtained in the same manner that we used for the previous questions. So we have a times 4 power n plus b times 6 power n. That is the solution for the homogeneous part. That depends on the nature of the roots of the equation, just like the ones that we have seen before. Further, this solution also has a second part called the particular part. Now, our function or recurrence relation is non-homogeneous in that we have a constant here. So this implies that the particular part of the solution will also be a constant. This is critical here. So the particular part of the solution, namely Sp of n, the particular part of the solution will take the same nature as the function on the right. So if we have a constant on the right, the particular part of the answer will also be a constant. If we have a linear function on the right, then the particular part of the solution will also be linear. If we have an exponential function on the right, then the particular part of the solution will also be exponential. Whatever function we find on the right, this particular part will take the same nature. Here we have the right hand side as only a constant 30. So our particular part of the solution will also take a constant nature, and we denote that by d naught. So since Sp of n is d naught and it does not depend on n, Sp of n minus 1 will also be d naught because it's a constant function. Sp of n minus 2 will also be d naught, another constant function. So we use all of this in the given recurrence relation to find the value of this constant. So this term is d naught. We have this also as d naught and also for this. So that's d naught minus 10 d naught plus 24 d naught equaling 30, which is the RHS of the recurrence relation. Simplifying, we see that 15 d naught is 30 or our d naught is simply 2. That has solved the second part of the answer for us. Now, once we know that, we can find the other two constants as well. So the solution of the recurrence relation is made of two parts, the homogeneous part, which we know already, and the particular part, which we just solved. So we have a times 4 power n plus b times 6 power n plus 2 as the answer. Now, we'll use the two information that were part of the question at s of 0 and s of 1. When n is 0, we have the term to be 2. So a times 4 power 0, b times 6 power 0 plus 2 is equal to 2. Or we just have a plus b is equal to 0, which means a is same as negative b. Further, if we have n is equal to 1, then s of 1 becomes 6. So a times 4 power 1 plus b times 6 power 1 plus 2 is equal to 6. Or in other words, 4a plus 6b plus 2 is 6. Or 4a plus 6b is 4. We already know that a is equal to negative b. Substituting, we see that b is 2 and a is negative 2. Therefore, we have the complete solution of the recurrence relation of this form. It is of this form where we have negative 2 times 4 power n plus 2 times 6 power n plus 2 as the closed form expression of the recurrence relation. So the closed form expression takes this particular definition here. Once again, you can note that this answer depends only on n and not on any other term. Therefore, we call this as the closed form expression. As usual, we'll try and verify and find out if this answer is right. Let's use 2 for n. So minus 2 times 4 square plus 2 times 6 square plus 2. That's minus 2 times 16, that's negative 32. 2 times 36, which is 72. And 2 added at the end gives us the answer as just 42. So S of 2 happens to be 42 from the closed form expression. Now, from the question, we see that S of 2 is 10 times S of 1 minus 24 times S of 0 plus 30. S of 1 was at 6. S of 0 was at 2. So that's 60 plus 30 minus 48, which is also 42. So the 42 that we obtained as the answer from the closed form expression matches the 42 that we obtained from the question. This means that our answer here is in fact perfectly right. Go to another problem. All right. In this question, we have tried to discuss a recurrence relation, which is a pretty interesting one. What we see here, once again, let's classify the recurrence relation. Type 1, it is, first up, we see that of order 2. It is a recurrence relation of order 2. Why do we say that? The smallest term involved in the sequence takes the value n minus 2. So n minus 2 is the smallest. So it is of order 2. And point number 2 is that it is again non-homogeneous because S of n depends not only on n minus 1 and n minus 2, but also on a function of n. This function here, this time, it's not a constant function, it's a linear function in n. The RHS is a linear function in n. Linear function in n. So now that we know we have completely classified the recurrence relation, we can start solving this. We'll solve this by finding the characteristic equation as usual. Since the recurrence relations of order 2, we have r square minus 13r plus 42 is equal to 0, expressing the characteristic equation of the recurrence relation. So once we have reached here, we can start solving step 1. Step 1 will mean that we solve the quadratic equation. The roots are real and distinct this time. Therefore, the homogeneous part of the solution, once again I recall, the answer will be of two parts, one for the homogeneous part and one for the particular part. The homogeneous part of the recurrence relation will take the form a times 6 power n plus b times 7 power n, since 6 and 7 are the roots, and the particular part will take a nature which is similar to the function on the RHS. We saw that the RHS is a function, a linear function of n. Therefore, it has a constant and it has an n term. So our particular part of the solution will also take the same nature, d naught plus d1n. The last problem, it was a constant, therefore it did not differ. It was d naught throughout. This time it's a linear function. So if the answer is d naught plus d1n for n, then for n minus 1, it becomes d naught plus d1 of n minus 1. And for n minus 2, it becomes d naught plus d1 times n minus 2. So substituting these into the actual given recurrence relation, we have 13 times sp of n minus 1 as negative 13 minus 13 d1n plus 13 d1. And 42 times sp of n minus 2 giving us 42 d naught plus 42 d1n, 42 d1n minus 84 d1. So using all these terms in the recurrence relation, we have a nice little expression for the particular solution of the problem. We have d naught plus d1n. We have minus 13 d naught minus 13 d1n plus 13 d1 from here. And 42 d naught plus 42 d1n minus 84 d1 from here. We can group the like terms. We can collect all constants together, all d1 terms together, all d1n terms together, and that will give us a nice, easy way to solve the equation. So they simplified down to 30 d naught plus 30 d1n and a 71 d1. From the question, this actually simplifies down to 19 plus 30n. So equating the like terms, the terms which have n's in them, we see that 31 d1n is same as 30n, which means the d1n, which seems, which clearly indicate that d1 is equal to 1, because the n terms, if you equate the coefficients, we see that d1 is equal to 1. Now, if d1 is 1, then when you equate the constant terms, we have 30 d naught minus 17 d1 is 19, or 30 d naught minus 71 itself is 19, or d1 is equal to 3. So we have our answers for d naught and d1. D naught is at 3 and d1 is at 1. Therefore, the particular part of the solution takes the form 3 plus 1n. So the constants that we set out to find in the previous screen, the constants that we set out to find here have been found. D naught is at 3, D1 is at 1. So this means we have the complete solution ready except for the constants A and B, and we'll find them here. So we have the solution as A times 6 power n plus B times 7 power n plus 3 plus n. And with this, we'll use the information that S of 0 is equal to 2. Since S of 0 is equal to 2, we have A times 6 power 0, which is A, and B times 7 power 0, which is B, plus 3 is equal to 2, or our first equation is A plus B is equal to negative 1. Similarly, if we say S of 1 is equal to 1, we have 6A plus 7B is equal to negative 3. So that gives us a nice little system of two equations and two unknowns. We can solve them easily. We can get the values of A and B as plus 3 and negative 4. So that gives us the complete solution of the recurrence relation of the form minus 4 times 6 power n plus 3 times 7 power n plus 3 plus n. This is again the closed form expression of the given recurrence relation. We'll just make a very short little verification of the same. Let's try and find what S of 2 is. Using 2 in the place of n, we have minus 4 times 6 squared plus 3 times 7 squared plus 3 plus 2, which comes down to 8. And now we'll go back to the recurrence relation that was part of the question and use 2 for n, where S of 2 is equal to 13 times S of 1 minus 42 times S of 0 plus 19 plus 30 times 2. That once again comes down to 92 minus 84, which is again 8. So the answer that we obtained from the closed form matches the answer that we obtained from the recurrence relation. And therefore, our recurrence relation that we found out here is in fact the perfectly correct answer. We have a couple of more problems to discuss. We'll do that next. The next recurrence relation is another peculiar recurrence relation. Let's try and classify this. Once again, it's pretty easy to identify that this recurrence relation is of order 2 because the smallest term that is involved is n minus 2. And it is also non-homogeneous. Why is this non-homogeneous? Because the definition for the recurrence relation involves not only the terms s of n minus 1 and n minus 2, it also involves a function of n, namely 3 power n. And that function is an exponential function. Now, this exponential function has to be dealt with very clearly. We'll see that as we proceed. So now that we have classified the recurrence relation, we can start solving this by identifying the corresponding characteristic equation. So we'll replace s of n by r squared, s of n minus 1 by r, and s of n minus 2 just by the constant 1. So we have r squared minus 8r plus 12 is equal to 0 as the characteristic equation of the recurrence relation. Now that we know the characteristic equation, we can actually set out and solve. We have the quadratic equation with roots 2 and 6. Therefore, the homogeneous part of the recurrence relation will take the form a times 2 power n plus b times 6 power n. Of course, these two constants will be evaluated by using the initial conditions at 0 and 1. Now, the interesting part here is that the particular part of the solution, which involves the function on the right, will take the form d naught times 3 power n because our RHS was an exponential function. The same exponential function will also be part of the particular parts of the solution. So since we had a 3 power n in the question, our answer will be a constant multiple of 3 power n. This is because of two things. One, the same index 3 must be repeated in the particular part of the solution. And number two, the roots of the characteristic equation are not the same as 3. Do you get the part? The roots here, 2 and 6, are not the same as 3, or the RHS 3 power n is not a power of 2 power, is not like 2 power n or 6 power n. We'll discuss that in detail in the next example. Since the roots of the equation are not factors of the constant on the RHS, our particular part of the solution will take this form. So if S of n is d naught times 3 power n, S of n minus 1 will be d naught times 3 power n minus 1. And similarly, we have d naught times 3 power n minus 2. We can find out what happens when we multiply by 8 and 12. So that gives us Sp of n minus 8 times Sp of n minus 1 plus 12 times Sp of n minus 2 is equal to 3 power n. We can factor out the 3 power n minus 2 as common here. This 3 power n minus 2 is common. And here I can write this n minus 1 as n minus 2 times 3 power 1 and n as n minus 2 times 3 squared. So when I factor out 3 power n minus 2 from every term here, I'll have these two in common, a 9, a 24, and a 12 inside the brackets. And on the right again, 3 power n, I'll write it again as 3 power n minus 2 and 3 square. Dividing both sides by 3 power n minus 2, we have an expression for d naught, and d naught is found to be negative 3. Once we have d naught, the particular part of the solution has been found out is negative 3 times 3 power n, and hence the complete solution of the recurrence relation is also ready except for the value of the constants a and b. So we have a times 2 power n plus b times 6 power n plus the product of minus 3 and 3 power n. As usual, we'll find a and b using the initial conditions given. We know s of 0 is 7. Therefore, we'll substitute 0 for n everywhere and obtain the equation a plus b minus 3 is equal to 7. And we also know s of 1 is equal to 15. Therefore, when we use 1 for n, we have 2a plus 6b minus 9 is equal to 15. Once again, this is a nice little system of two equations and two unknowns which can be solved. We can multiply equation 1 with 2, subtract, and obtain the value of b as 1 after eliminating a. So if b is 1, we can get a as 9. So with a as 9 and b as 1, we have the complete solution of the recurrence relation as 9 times 2 power n plus 1 times 6 power n plus 3 power n times negative 3. As usual, we do a very short verification of this answer by finding what s of 2 is. When n is equal to 2, we have 9 times 4 plus 1 times 36 minus 27, which is 7 2 minus 27, which is 45. And now we'll find out s of 2 from the given recurrence relation. And we see that s of 2 is 8 times s of 1 minus 12 times s of 0 plus 3 squared, which is 9. That's 120 minus 84 plus 9, which is again 45. So the 45 from the closed form expression matches the 45 from the recurrence relation, which means the answer that we obtained a couple of slides back is perfectly correct. So this answer is the solution of the recurrence relation since it represents the closed form expression of the sequence. Now, we'll just discuss one last problem to discuss a very particular case here. Let's understand this recurrence relation again. We have a recurrence relation of order 2. This is of order 2 because the smallest term in the sequence is n minus 2. And we have a non-homogeneous recurrence relation which can be clearly identified by the 2 times 7 power n as part of the RHS. And we also see that this RHS function is an exponential function. So the corresponding particular part of the solution will have to be of the same nature. So now that we have done all this, we can proceed to solve by finding the characteristic equation. We'll just replace s of n by r square, s of n minus 1 by r, and s of n minus 2 by the constant 1. So we have r square minus 12r plus 35 is equal to 0 as the characteristic equation of the given recurrence relation. Now the interesting thing to note here is that this equation will have 5 and 7 as the roots, and this 7 is also a factor of the function on the RHS. Now, this was not the case in the previous problem where we had 2 and 6 as the roots and the RHS was 3 power n. So they had nothing to do with 2 and 6. Here though, the roots are 5 and 7 and one of the roots here is a factor of the function on the right. In such cases, we'll have to be careful when we define the particular function of n and we'll write it as n times 7 power n times d naught. Last time it was only d naught and 7 power n. This time the addition, the inclusion of n is because one of the factors is, is a one of the roots is a factor of the function on the right. Suppose both the roots are factors of the function on the right, then we'll have to write n square times 7 power n times d naught. That is when both roots, let's say we have 7 and 7 as the roots, and we have 7 power n on the right. And in that case, we'll write n square times 7 power n times d naught. That's not the case though here. So we have only n times 7 power n. So with that in mind, we'll proceed to the step 1. We have framed the equation and we can solve it. The roots are real and distinct. Therefore, the homogeneous part of the solution will be a times 5 power n plus b times 7 power n. Proceeding further, because one of the roots of the equation is a factor of the function on the right, we have SP of D and SP of n as D naught times n. This is the newly included part times 7 power n. So SP of n minus 1, you will replace n by n minus 1. SP of n minus 2, you will replace n by n minus 2. So all these are easy to follow. Substituting them in the equation, we have 12 times s of n minus 1 as 12 times d naught times n minus 1 times 7 power n minus 1, and 35 times s of n minus 2 as 35 times d naught times n minus 2 times 7 power n minus 2. Substituting them all back into the equation, we have this big expression to solve for. Of course, again, I'll write 7 power n as 7 power n minus 2 times 7 squared, 7 power n minus 1 as 7 power n minus 2 times 7 power 1, and this I need not factor. So the n is common, the d naught is common, the 7 power n minus 2 is common. If we factor all of them out, we have this nice little expression which can be solved to obtain the value of d naught as 7. So once you know d naught as 7, we have solved for the particular expression, particular part of the solution of the given recurrence relation. We have 7 times n times 7 power n, which means we have n times 7 power n plus 1. So the general solution of the recurrence relation will take this form: a times 5 power n plus b times 7 power n plus n times 7 power n plus 1. Of course, we can find a and b by using 0 for n. So S of 0, we use 0 for n. We have a times 5 power 0, b times 7 power 0, plus 0 times 7 power 0 plus 1. So a plus b is equal to 1 is our equation number 1. And then when we use 1 for n, we have 5a plus 7b plus 1 times 7 squared. 49 is equal to 60. That's equation 2. That's another system in two equations and two unknowns, which can be solved easily. Solving them returns the values of a and b as -2 and +3. So our closed form expression of the recurrence relation takes this form. It's -2 times 5 power n plus it takes the form -2 times 5 power n plus 3 times 7 power n plus n times 7 power n plus 1. Of course, we'll just do a customary check of the answer. We'll try and find s of 2. Substituting 2 for n, we'll have -50 plus 147 plus 2 times 7 cubed, returning 783 as the answer from the closed form expression of the solution. And from the question, we have s of 2 as 12 times s of 1 minus 35 times s of 0 plus 2 times 49, which is again 783. So the answer from the closed form expression here matches the answer from the given recurrence relation. This implies that our solution here is in fact perfectly correct. Hope you enjoyed this video.